Welcome to this video on fiber optic communication. In this video, we will be discussing about dispersion, the various types of dispersion, and also the characteristics of single mode fiber. Dispersion causes distortion of both analog and digital signals as it propagates in an optical fiber. Considering a pulse that is launched into a fiber, dispersion causes broadening of the pulse as it travels along the fiber. And this broadening causes overlapping of pulses and which results in intersymbol interference. This limits the bit rate and the bandwidth or the capacity of the fiber. As can be seen in the figure, the data 1011 bits are being transmitted, the pulses are being sent. As the pulses propagate along the fiber, due to dispersion, they get broadened. So, broadening of these pulses cause overlap of pulse as can be seen in the second figure. As the pulses propagate further down the fiber, the broadening of the pulse increases and the overlapping increases to such an extent that the pulses become indistinguishable. Therefore, at the receiver end, the pulses are indistinguishable and result in error. So, this limits the data rate at which the pulses can be transmitted, and therefore it limits the bandwidth that can be supported by the fiber. So, considering optical pulses and considering there is no overlapping, then the digital bit rate can be, it is less than or equal to 1/2 tau, where tau is the input pulse duration and 2 tau is the pulse duration after broadening. But considering Gaussian pulses with RMS width of sigma, where overlapping is permitted such that there is no SNR penalty. In that case, the maximum bit rate can be given by 0.2 by sigma, and for non-return to 0 coding, the bit rate, maximum bit rate is twice the bandwidth, and for return to 0 coding it is equal to the bandwidth. So, the amount of pulse broadening depends on the distance the pulse travels in the fiber. So, as the pulse travels along the fiber, the effect of dispersion causes broadening of the pulse. So, and the broadening depends on the dispersion per unit length of the fiber. This restricts the information capacity of the fiber, and the information capacity can be given by bandwidth into length product. This picture shows the dispersion for the different types of fibers. As can be seen, a multimode step index fiber has the maximum dispersion and the single mode step index fiber has the minimum dispersion. So, the pulses are launched into the fiber and the output pulses are indicated due to broadening. The pulse broadening in a multimode graded index fiber is lesser compared to that of a multimode step index fiber. And the bandwidth length product, the capacity of a fiber for the multimode step index, graded index and single mode step index fiber is given. It is seen it is maximum, the bandwidth length product is maximum for single mode step index fiber. Next we shall see the causes or the different types of dispersion. Dispersion can be grouped as intermodal dispersion, intramodal dispersion and polarization mode dispersion. Intermodal dispersion is dispersion between the various modes, and intramodal dispersion is dispersion within a mode, and that can be further classified as material dispersion and waveguide dispersion. And then we have the polarization mode dispersion. First we shall discuss about what each dispersion is, and then we will look into the mathematical analysis of them. So, first considering intermodal dispersion. Intermodal dispersion is significant in multimode fibers, and it is due to the many modes present in the fiber. The different modes, they travel along different paths, and therefore they take different times to travel and reach the destination at different time intervals, and this causes dispersion. And intramodal dispersion, or it is also called chromatic dispersion. Chroma means color, which is wavelength dependent. So, this is a dispersion that is dependent on the wavelength of light. So, here spreading occurs because the source emits light over a finite spectral width. So, this is significant in single mode fibers. So, though in a single mode fiber the modes travel along the same path, the dispersion occurs because of the various wavelengths or frequency components in the mode, and this is further classified as material dispersion and waveguide dispersion. Material dispersion, it is caused due to the dispersive property of the waveguide material itself. It is because of the dependence of refractive index n on the wavelength. So n is a function of wavelength. Therefore, though all the frequency components travel along the same paths, the variation in refractive index for different wavelengths causes different velocities of travel for the different frequencies, and this causes spreading of the pulse and thereby dispersion. Waveguide dispersion, it is due to the guidance effect within the fiber structure. We know in an optical fiber, when light is launched, around 80% of the light travels along the core and 20% along the cladding, and therefore the effective refractive index lies between the value of the refractive index of the core and cladding, and depends on the amount of power that propagates in the core and in the cladding. This power distribution in the core and cladding is itself a function of wavelength. So different wavelengths cause different amount of powers to travel in the core, and therefore based on the wavelengths, the effective refractive index n effective changes, and therefore beta effective, the effective propagation constant changes, and this results in dispersion. So beta is a function of wavelength. So waveguide dispersion is caused because the effective refractive index n effective is a function of wavelength. Next we have polarization mode dispersion. This is because of fiber birefringence, that is two different refractive indices along the different axes. This causes the two orthogonal components to travel at different velocities, causing dispersion, and polarization mode dispersion is critical for high bitrate long distance transmission. Now we will look into the mathematical analysis of each of these dispersion. First, considering intermodal dispersion or modal delay, which occurs in multimode fiber. As you can see in the picture, the different modes travel along different paths. So the ray that travels along the center of the axis takes the shortest path, whereas rays that are reflected from the core cladding surface, they take longer paths. So the total delay difference is the time difference between the longest ray congruence and the shortest ray congruence, that is between the ray that travels and gets reflected at the core cladding interface and takes a long path, minus the one that takes the shortest path which travels along the axis of the fiber. Now looking into the figure, considering a distance of travel of L along the axis, T minimum, we know time is distance by velocity, so it is distance L by velocity. Velocity is, we know n is c by v, so substituting that we have L by c by n1. And similarly, the maximum distance is the distance travelled by the ray that goes to the outer core cladding interface, and so considering that to be x, from the picture it is seen that cos theta is L by x, and from that x is L by cos theta, substituting that value to determine the time taken as distance by velocity. Now the delay difference is difference between T max and T minimum. Solving it, we get delay in step index fiber is L n1 delta by c, or that is equal to L na square by 2 n1 c. So it is seen that the delay is proportional to delta, that is the relative refractive index difference. So the relative refractive index difference should be small so that the delay difference is reduced and therefore dispersion is minimized. But when the value of delta is small, the fiber becomes more weakly guided and therefore more energy leaks into the cladding, and also this causes reduction in acceptance angle and numerical aperture, and therefore launching of light into the fiber is difficult. So an optimal value of delta has to be chosen. The RMS pulse spreading for a step index multimode fiber is given. Next, looking into a graded index fiber. Compared to a step index fiber, the intermodal dispersion for a graded index fiber is lesser. Let us see why. Because for the because for a graded index fiber, the refractive index in the core varies radially. Therefore, we know the ray that passes along the axis of the fiber travels the shortest distance, and in a graded index fiber, the refractive index in the core is the maximum, and it reduces as we move outward radially. And therefore, the other rays that travel a longer distance towards the outer of the core, they will be encountering lesser refractive index of the material. So, this variation in path distance difference is compensated by the variation in refractive index difference. So, the refractive index is maximum along the axis, which is the shortest distance, and it is minimum radially outward for the ray that takes longer paths. So, this is compensated. The difference in path distance is compensated by the difference in velocities with which they propagate, and this results in lesser intermodal dispersion. So, using ray theory approach, the delay difference for graded index fiber is determined and the pulse spreading is determined, and it is observed that for a parabolic refractive index profile where alpha is equal to 2, this gives the optimal value for minimum dispersion in a fiber. Next, we shall consider intramodal dispersion or chromatic dispersion. So, this is a dispersion that occurs within a mode. Intramodal dispersion occurs due to the finite spectral width of the optical source. An optical source practically does not emit light in just a single wavelength. Rather, it emits light over a finite spectral width, as can be seen in the figure. The spectral width of laser is much lesser compared to the spectral width of LED. So, this finite spectral width, this causes the different frequency components to be emitted, and the different frequency components propagate with different velocities, and this causes dispersion. And this delay difference or this dispersion is due to material dispersion and waveguide dispersion. Before looking into material and waveguide dispersion, we shall get familiar with some of the terms and derive the parameters for general parameters for intramodal dispersion, and then we shall take up material and waveguide dispersion separately. So, first is group delay. This is again because the source emits light of finite spectral component. The various frequency components, they travel at different velocities and take different amounts of time to travel a certain distance. So, this causes group delay. And next is phase velocity. If the light emitted is monochromatic, that is only one wavelength, then the wavefronts or points of constant phase, they will travel with the phase velocity of Vp is omega by beta. Next, group velocity. We know that a source does not emit light at a single frequency but over a finite spectral width. So, group velocity is defined the velocity at which energy of a pulse propagates in a fiber. So, since the source emits light over a width of spectral width, a group of waves with similar frequencies, they travel forming a packet of waves, and these waves, they do not travel at the velocity of individual waves, but rather they travel at a group velocity, which is given by Vg is equal to delta omega by delta beta. As you can see in the picture, two different frequencies components waves are shown, and they travel as a packet of wave, as a group, and this group travels at a group velocity, not at the velocity of the individual waves. Next, we shall look into pulse broadening because of group velocity. So, the delay per unit length tau g by L is equal to 1 by group velocity, that is Vg. Vg can be determined as d omega by d beta, and substituting the values and reducing, we get tau g by L, that is 1 by Vg is minus lambda square by 2 pi c into d beta by d lambda. As we can see from the expression, the group velocity and the group delay, they are functions of wavelength lambda. That is, the different wavelength components propagate with different velocities. So this results in difference in time delay between the different wavelength components, and this causes pulse spreading and thereby dispersion. Now considering a source that emits light at lambda naught with spectral components that are delta lambda apart, the total delay difference delta tau over a distance L because of the spectral width is given by delta tau is equal to the group delay per unit wavelength into the total spectral width. So reducing that we get an expression, and we can also reduce it in terms of angular frequency. Here the term d square beta by d omega square is called the group velocity dispersion or beta 2, and it is a very important parameter that determines how much a pulse broadens as it propagates along a fiber. So the approximating the spectral width by its RMS value sigma lambda, we get pulse spreading as d tau g by d lambda into sigma lambda, and the dispersion is given by this expression. It is minus 2 pi c by lambda square into beta. Dispersion defines the pulse spread as a function of wavelength, and its units is picosecond per nanometer into kilometer. And this intramodal dispersion is due to material dispersion and waveguide dispersion, which are both interdependent. But approximating, we can consider or determine the values of material dispersion and waveguide dispersion separately, and the total dispersion can be taken as summation of the two. Next we shall consider material dispersion. Material dispersion occurs because of the dependence of the material on the wavelength. So the dependence of refractive index of a material n on wavelength. So beta is equal to nk. N is not a constant here, it is a function of wavelength n of lambda, replacing that and determining group velocity with that, we can find out group velocity and the material delay time as given in the equations. And from this the pulse spread can be determined to be sigma lambda L into d material of lambda, that is the material dispersion. As can be seen in the graph, the refractive index for silica, it varies with the wavelength and it decreases for longer wavelengths. Considering waveguide dispersion, so neglecting material dispersion, waveguide dispersion can be determined, and waveguide dispersion is significant for single mode fibers because multimode fibers, most of the modes they propagate far off from the cutoff frequency, and therefore waveguide dispersion can be ignored. So considering normalized propagation constant and getting the propagation constant beta with respect to that, the group delay due to waveguide dispersion is determined. And we know normalized frequency V is equal to 2 pi a by lambda into root of n1 square minus n2 square. Using that expression, we can express the group delay in terms of normalized frequency, and the pulse spread is determined, where dWg is the dispersion due to waveguide dispersion. So this graph shows the total dispersion, which is due to material dispersion and waveguide dispersion. It can be observed that at around a wavelength of 1310 nanometer, the material dispersion and waveguide dispersion are of equal values, so they cancel out and the dispersion is 0. So we have 0 dispersion at 1310 nanometers, and at lower wavelengths and higher wavelengths, the material dispersion value dominates. The next dispersion is polarization mode dispersion. It is caused due to fiber birefringence, that is two different refractive indices along the axis of the fiber, and this is critical for high bit rate long distance transmission. And the internal and external factors that cause polarization mode dispersions are geometric irregularities, internal stress, bending, twisting, so on. So as we have seen in the previous video on mode theory, the fiber birefringence, that is two different refractive indices along the two axes of the fiber, cause the two degenerate modes, which are orthogonal polarization modes, to propagate with different velocities. This difference in velocities cause a difference in phase, and it also causes a difference in time delay, which results in polarization mode dispersion. As can be seen in the picture, the two modes that are launched into the fiber, as they propagate along the fiber, due to fiber birefringence, the velocities of the two modes varies, and therefore a difference in delay, a time delay occurs given by delta tau polarization, that is equal to L by Vgx along the x axis and minus L by Vgy, the delay due to velocity along the y axis. So this causes dispersion or spreading of the pulse, and that is called polarization mode dispersion. So summarizing the different types of dispersions, we have intermodal dispersion, intramodal or chromatic dispersion, and polarization mode dispersion. In multimode fibers, intermodal dispersion is significant. So the intermodal dispersion for a graded index fiber is lesser compared to that of a step index fiber, but the decrease in dispersion in a graded index fiber is limited because of profile dispersion. That is, it is difficult to maintain the difference in refractive index radially over long distances of fiber, and this results in profile dispersion. And the profile dispersion, the profile is normally optimized for a certain wavelength, and a small variation in wavelength drastically increases the dispersion and decreases the bandwidth that can be supported by the fiber. So profile dispersion is significant in case of multimode graded index fibers. Coming to intramodal or chromatic dispersion, the material dispersion is large for a multimode fiber and waveguide dispersion can be neglected. Whereas for a single mode fiber, the waveguide dispersion value is significant and more or less equal to the material dispersion. And polarization mode dispersion is significant in case of high data rate transmission. So summarizing, multimode fibers, intermodal dispersion and material dispersions are significant. Whereas for a single mode fiber, material and waveguide dispersions are important, and for long distance high bit rate transmission, polarization mode dispersion is also to be considered. Next we shall look into some of the characteristics of single mode fiber. So first we shall see refractive index profile. So dispersion limits a long distance high speed transmission of data. And we know for step index silica fiber, the dispersion is minimum at 1310 nanometers and attenuation is minimum at 1550 nanometers. Manufacturers, when they manufacture a fiber, they are concerned about chromatic dispersion and polarization mode dispersion. Okay, to have maximum distance travel or transmission distance of fiber, it should be operated at the minimum attenuation value, that is at 1550 nanometer. But then dispersion is not minimum at that value, therefore fibers are designed to have minimum dispersion at 1550 nanometers, that is minimum dispersion at the minimum attenuation value. Material dispersion is function of the material composition, and waveguide dispersion, it is a function of the core radius, the refractive index profile, relative refractive index difference, so on. So it is hard to alter the material dispersion, but it is easy to alter the waveguide dispersion. Therefore, the dispersion is altered by keeping the material dispersion as it is and altering the waveguide dispersion. So these are the different types of fibers that can be obtained. Single mode step index fibers are normally operated at 1310 nanometers. So we have optimized fibers. The match cladding and the depressed cladding type as shown in figure A, and the 3-dimensional view of the refractive index profile shown over here. And next we have the dispersion shifted fibers, where dispersion is shifted to the 1550 nanometer wavelength. So the 3-dimensional view of that is indicated. Next is the dispersion flattened fibers, where the dispersion is flattened over a wide range of wavelengths. Then we have the large effective core area fiber, where the core area is made large enough so that nonlinear effects are minimal. The two graphs show the dispersion as a function of wavelength. The first graph on the right shows the individual material and waveguide dispersion. So, the material dispersion is plotted and the waveguide dispersion for the different types of fibers, single mode step index fiber, then the dispersion flattened fiber and dispersion shifted fibers. The graph on the left hand side shows the total dispersion, the sum of the material dispersion and the waveguide dispersion for a step index fiber, for a dispersion shifted fiber and a dispersion flattened fiber. Observe for a dispersion shifted fiber, the dispersion has been, or the minimal zero dispersion has been shifted to 1550 nanometer. For wavelengths greater than 1550 nanometers, the dispersion is positive, and for wavelengths less than 1550 nanometer, the dispersion is negative. But for WDM systems which are closely placed, this altering positive and negative dispersion introduces nonlinear effects and affects the transmission in the fiber, and therefore non-zero dispersion shifted fibers are manufactured where a small amount of dispersion, either positive or negative dispersion, is introduced so that the nonlinear effects are minimized. Then coming to dispersion flattened fibers, the dispersion flattened fibers, the dispersion should be maintained over a wide range of wavelength and therefore they are difficult to manufacture. Next we shall consider cutoff wavelength. We know for a single mode fiber, for the normalized frequency equal to 2.405 gives a single mode fiber, and we know V is equal to 2 pi a by lambda into root of n1 square minus n2 square. From that the value of lambda c, cutoff wavelength for single mode fibers, can be determined. And the cutoff wavelength for the first higher order mode, that is LP11, is important in single mode fibers because this separates single mode fiber from multimode fiber. For a single mode fiber, the fundamental mode LP01 propagates and the next higher mode is LP11. So, this LP11 cutoff wavelength determines whether the fiber is going to be single mode or multimode. Around the cutoff region, the power of an LP11 mode is not tightly bound to the core, but it is spread over the cladding also. So, its attenuation is affected by fiber bends, etc. Now, to determine the cutoff wavelength practically, a single mode fiber is taken and one or more 14 centimeter loops are made so that only the fundamental mode and the next higher order mode LP11 and LP01 are existing in the fiber. Next, light is launched into the fiber to excite both the modes equally, and P1 of lambda is measured around the expected cutoff wavelength. Next, smaller loops of 30 mm radius are made so that only the fundamental mode exists, and then the power around the same wavelength range P2 of lambda is determined, and the ratio between P1 and P2 is calculated. The relative power R lambda is plotted for the various wavelengths, and the point, upper wavelength point where the power level goes to 0.1 dB is noted, and that is the cutoff wavelength, and it is normally in the range of 1100 nanometer to 1280 nanometers. Next, to determine the dispersion calculation. So, we know in single mode fiber the dispersion is mainly because of chromatic dispersion, that is of material dispersion and waveguide dispersion, and it is given by this expression, and broadening of pulse occurs over a distance L. As you can see from the graph, the dispersion varies with wavelength and also the different types of fibers, and the dispersion is also affected by the bandwidth of the source. If the bandwidth or spectral width of the source is larger, then the dispersion is higher and the bandwidth supported is lesser, and it drastically changes from the optimal value of wavelength. Even a slight deviation from the optimal value of wavelength decreases the bandwidth drastically. So, to determine the dispersion or calculation of dispersion, standard formula are recommended depending on the type of fiber that is used and the wavelength range of operation. Next, moving on to mode field diameter. We know for a single mode fiber, the energy of a pulse is not concentrated in the core itself, it is spread into the cladding also. So mode field diameter is a measure of the width of distribution of electric field intensity, and it is used to predict fiber properties such as splice loss, bending loss, cutoff wavelength, etc. And this graph over here shows the mode field diameter for the various wavelengths for the different types of fibers. So in this video, we have discussed about dispersion, the different types of dispersion and the mathematical analysis of the dispersion. And we have also seen the characteristics of single mode fiber. These are the references. Thank you.